Okay, in the next problem, the figure above shows an above-ground swimming pool in the shape of a cylinder with a radius of 12 feet and a height of 4 feet. The pool contains 1,000 cubic feet of water at time t equals 0. During the time interval from 0 to 12 hours, water is pumped into the pool at a rate p of t cubic feet per hour. The table above gives values of p of t for selected values of t. During the same time interval, water is leaking from the pool at a rate of r of t cubic feet per hour, which is r of t equals 25 e to the negative 0.05 t. So we note the volume V of a cylinder is given by V is equal to pi r squared h. So first thing we want to do is use a midpoint Riemann sum with 3 subintervals of equal length to approximate the total amount of water that was pumped into the pool during the 12-hour time span. Show the computations that lead to your answer. So we take the 12-hour period of time and we break it in, divide by 3, so we'll have intervals of 4 sub-intervals of 4 hours, from 0 to 4, from 4 to 8, and from 8 to 12. And the left endpoint in the first subinterval is 0, the midpoint is 46, the right endpoint is 53. We're going to use the midpoint for this. So for the first subinterval it's 46, for the second subinterval 57, for the third subinterval 62, and we want to approximate the total amount of water that's pumped into the pool. So we say integral from 0 to 12 p of t dt is roughly equal to, factoring out the 4 since we have a subintervals of equal length. And so that gives us 660 cubic feet. Part B, calculate the total amount of water leaked out of the pool during the time interval from 0 to 12 hours. For this we'll need to use the graphing calculator. And so we put that into y1, 25 e to the raised to the negative 0.05 x power. And so we don't have to worry about a window. I'll use fn int. Second, quit, math, option 9, have vars, y vars, function y1, comma, x, comma, 0, from 0 to 12, and we get 225.594. Now for part C, we want to use the results from A and B to approximate the amount of water in the pool at time t equals 12 hours. So we have the initial amount, which was 1,000 cubic feet. Then we added 660 cubic feet, and we subtract 225.594. So we're at 1,000 plus the integral from 0 to 12 of p of t minus r of t dt. That gives me the net change in the volume of water is equal to 1,000 plus, is roughly equal to 1,000 plus 660 minus 225.594. And that gives me 1434.406. And they want that rounded to the nearest cubic foot, so that would just be 1434 cubic feet. All right, next, find the rate at which the volume of water in the pool is increasing at time t equals 8 hours. How fast is the water level in the pool rising at t equals 8 hours? Indicate units of measure in both answers. So we're looking for dv dt, the volume, rate of change of volume with respect to time, and we're looking for dh dt. So we'll start off with our volume equal to pi r squared h, but here the volume is a constant 12 feet. And so we end up with 144 pi h. We take the derivative of both sides with respect to t. Now the volume of water in the pool on one hand is pi r squared h. On the other hand, it is that formula 1,000 plus integral from 0 to 12 p of t minus r of t. Sorry, for any time t, we're not going to use 12 there. So it's slightly different than the calculation above. So I'm going to have 1,000 and then integral from 0 to t of p of x minus r of x dx. And by the second part of the fundamental theorem, that's just going to be the derivative of that is just p of x minus r of x. And so that derivative at time t equals 8 is just p of 8 minus r of 8. We're given that p of 8 is 60 from the table. And I'll continue in the next video.